As a civil engineer, one of your core jobs is to track the exact journey of a single storm, from the sky, across the ground, through the pipes, and into the river network. This animated graph on the left shows a mass curve of rainfall next to a standard bar chart hyatograph on the right. This mass curve is where our calculation starts. Because the mass curve plots the cumulative rainfall over time, the math here is highly practical. By calculating the slope of this line, the rise over run, you determine the precise rate of rainfall, which we call the storm's intensity. A positive, steep slope means active rain is falling. A flat horizontal line indicates a dry period where the cumulative total holds steady. And since rainfall cannot run backward into the clouds, this curve will never slope downward. A negative slope is physically impossible. Deriving the correct intensity from this mass curve is the required first step. You must know exactly how much water is falling from the sky before you can figure out how much will hit the ground and become surface runoff. Once we have that measured rainfall data, we have to convert it into a predictive total flood hydrograph. To do this accurately, engineers follow a strict four-step sequence, frequently tested as the PRSQ order. Step 1 is P, obtaining the hyatograph. This locks in our baseline data, showing the specific distribution of the storm's intensity over time. Step 2 is R, estimating losses. Not every drop of rain reaches the river. We subtract the initial abstraction, water trapped in puddles or on leaves, and the infiltration into the soil. What remains is our actual rainfall excess. Step 3 is S, applying the unit hydrograph method. We take that remaining rainfall excess and mathematically convert it directly into surface runoff. Finally, step 4 is Q, adding the base flow. The river wasn't entirely empty before the storm started. By adding the existing groundwater flow to our calculated surface runoff, we get the complete total flood hydrograph. By following this exact sequence, P, R, S, Q, you account for every environmental factor in the precise order it occurs in nature. Predicting natural river levels is only one part of the job. We also have to size physical infrastructure. To design a storm sewer for a specific plot of land, engineers use the rational method, where the flow rate equals the runoff coefficient times rainfall intensity times area. Consider this test scenario. We have a rectangular plot of land with an outfall drain at one corner. The water takes different amounts of time to reach the drain from each corner: 10 minutes from A, 15 from C, 20 from B, and 25 minutes from D. The storm's intensity for this plot follows the formula 25 over T plus 10. Pause the video for a moment. To design the system for maximum flow, which of those 4 times should you plug in for T? You must use the longest time of concentration, which is 25 minutes. The sewer will only experience its absolute maximum flow when the water from the furthest corner finally reaches the drain, meaning the entire plot is contributing simultaneously. Plugging that 25 into our equation gives us 25 over 35, resulting in a design intensity of roughly 0.714 centimeters per hour. Designing your infrastructure around the longest time of concentration secures your safety margin. If you calculate based on a shorter duration, the system will overflow the moment that far corner finally catches up. Once the water leaves the local plot and hits the larger river network, we enter the final stage, flood routing. This calculates how a flood wave changes its shape and speed as it travels downstream. There are 2 major philosophies for routing. Hydrologic routing relies on the continuity equation, balancing inflow, outflow, and storage. The modified Pohl's method belongs here, and it is the standard tool for routing floods through a level reservoir. This diagram illustrates why rivers require a different hydrologic tool. Unlike a flat reservoir, a flowing channel develops dynamic volume shifts, modeled here as prism storage and wedge storage. To account for these shifts during channel routing, we use the Muskingum method. On the right side of the screen is hydraulic routing. This incorporates both the continuity equation and the physical momentum of the water. The primary technique used for this complex flow is the method of characteristics. Engineers must categorize these tools properly: hydrologic methods for mass balancing in reservoirs and channels, and hydraulic methods for precise momentum-driven measurements. We've covered a dense sequence of formulas and methods. Let's lock in that terminology with a rapid-fire matching test, mirroring the exact structure of an AEE exam. Look at these two columns. Map reservoir routing, channel routing, and hydraulic routing to their correct operational methods. Reservoir routing connects to the modified pools method. Channel routing connects to the Muskingum method. And hydraulic routing demands the method of characteristics. This is your summary of the core principles. Take a screenshot of this cheat sheet right now to keep for your review notes. You now know how to track a storm from the initial mass curve down into the sewer design and through the routing network. Good luck on your exams.